All right, so welcome back, everyone, to the review session. So now that we've finished our discussion of language classification, right, we're going to move on to designing Turing machines, right, to show that given languages are decidable. So that's going to be the next exercise. We're going to want to design a Turing machine which decides the following language L, where L is the language containing strings, W hash flip W, where these strings are in 0, 1. And the flip of W is an operator that does exactly what you think. It takes a 1 and it flips it to a 0, and it takes a 0 and it flips it to a 1, right? So 1, 1, 0, right? So that means that, you would want to accept a string like 1001 hash 0110, right? But not something like 1001 hash 0011, right? Because this is not equal to the flip of this guy, right? So how are we going to design a Turing machine that recognizes this language? By the way, we're assuming that this hash is kind of like a special symbol that's reserved for the tape. And so you can only have at most one of these symbols in the input string. If there's more, then your Turing machine should also reject. Okay. So how are we going to do this? The logic is going to be actually quite similar to recognizing something like W hash W. It's just that the logic is going to be a flip, I guess pun intended here. And so the way that we're going to do that is, suppose I have 1001 hash 0110 and blanks to the left and to the right. Then essentially what I need to do is I need to create sort of a while loop where essentially what I do is, I check, what I have here. So I see that I have a 1. I mark this with an X. I loop through my string until I reach the second half, where I pass the hash. And I check that the first unmarked string past that, the first unmarked letter, past the hash is a 0, right? Because it should be the flip of 1. So if this truly is a 0, then I'll mark it. And then I will loop back here and start the process over again, right? So this is why I'm saying I'm creating a while loop, right? Because I'm doing this as long as I have things that are unmarked, right? Here I have a 0, so again, I'll mark it with an X. But now once I'm looping here, what I'm looking for in this part of the string is not a 0, but a 1, right? Because the flip of 0 is 1. So I will only keep going. My computation only keeps going if when I see this first unmarked letter, it's a 1, right? And so I keep this going, right? I keep this going until the stopping condition being, I sort of mark this X, this 1 with an X. I've marked this 0 with an X. I loop back, right? Then, this has been marked with an X, and I'm looking for the next thing to mark. I move right, and I see a hash, right? So once I move right and I see a hash, that tells me that I should stop. And, not literally stop. I should first check that the remainder of this string, there's no like extra 0 or 1 here. And so that I've marked everything here with X's, and that the next thing I see is a blank, right? So that's essentially going to be the idea behind the Turing machine. Now, because I have sort of two different logics based on whether I'm reading a 1 or a 0, that essentially tells me that I'm going to have two branches in my Turing machine, right? So I'm going to start my Turing machine by drawing the start state. And from the start state, I'm going to have like the logic of I see a 1, so therefore I look for a 0. And I'm also going to have the logic for I see a 0, and so I look for a 1, right? And then once I get, to this common state here, I'm just going to loop back until I read sort of an X. I'll move right, and then I'll start my loop again here. Okay. So what is this going to look like a bit more concretely? So I'm here, and let's do the top branch. So if I see a 1, then I'll mark it with an X, and I'll move my pointer right. Then, okay, nice. I've seen this one. I've marked it with X. What I want to do next is I want to go through the rest of the zeros and the ones here, right? So that's why here I'm going to have a loop for zeros and for ones, right? Then at some point, if I do have like a string W hash flip W, at some point I'm going to see the hash, right? So the hash should be eventually seen, at which point I'll move right. But now I'm going to change logic to be like, okay, now I'm looking for the first thing that's not marked with an X. So here I'm going to loop through the things that may already have been marked with X's, right? So maybe I have already marked 2 things with an X. So I'm looping through the stuff that's already been marked. And what I'm looking for here, right? What I'm looking for is for the next unmarked thing to be a 0, right? So I only keep going if I see a 0, right? So if I see a 0, then I'll mark it with an X. And now it's time for me to sort of start closing this while loop to go back all the way to the start of the machine, right? So I'm going to go left, and I'm going to start moving back, right? So I'm going to have to move back through my X's. Then eventually I should, given that I saw a hash on the way here, I should see a hash on the way back, right? And then once I'm here, right? Once I'm here and I've moved left from the hash, then I want to go through the things that haven't been marked yet, because I'm looking. Essentially, what I'm doing is I'm looking for the first X, which is going to tell me I've overshot by 1, and I should move back right so I can start the whole loop all over again, right? So that's what I'm going to do. I'm going to move left through the unmarked zeros and ones. And once I see an X, that tells me that I've overshot, right, by 1. So I should not touch this X, move my pointer right. And now basically I am back here, right? And now it's exactly the same logic, right? It's exactly the same logic, but just with 0 and 1, right? So I'm going to go through this a bit quicker. I'm just going to quickly copy it. So if I see a 0, mark it with an X, and go through the unmarked zeros and ones. Then eventually I should go through the hash. I'll go through the stuff that I already marked. And eventually I should see a 1, right? If I don't see a 1, then I'll just halt here and reject. If I do see a 1, though, then I can go here to start my process of looping all the way back and finding the place that I sort of last marked X on the left part of the string, right? So if I see a 1, right, a 1 because I'm doing flip of 0, then I mark it with an X and I move left, right? So then, with this logic, I was back here, then I moved here. From here, I marked this with an X. Then I went through the zeros and ones with this state. I went through the hash with this state. And I went through the already marked X's here, looking for the first thing that's unmarked. It happens to be, I'm very lucky, happens to be a 1. So then I mark the 1 with an X, right? And then I start looping back through the X's, then through the hash, and then through the remaining, the unmarked zeros and ones. I overshoot, right? So I get to this X, that means I overshot, so I move right, and now I start the loop all over again, right? So I close the while loop, right? And like I said, the stopping condition, right? The stopping condition is I do this thing, right? I think that I've overshot, and so I move right, right? But now instead of seeing a 1 or a 0, I see a hash, right? So that's why it's very nice to have a hash and not just W flip W, because you don't have to guess where the middle is, right? So that it's sort of like a way to make the problem slightly easier and more doable in an exam. I have the hash to tell me, okay, yes, I have reached the sort of middle, right? So if I see the hash at this point, then I should just check, right? I should just check that I have x's and then a blank, right? So that's what I'm going to do. I'm going to loop through the x's. And the only way that I'm going to get to my accept state, right, the only way that my Turing machine is going to accept is if I see a blank. Right? If I do, then that means that, by this logic, right, by this logic, I was marking ones with zeros and then zeros with ones. And I was doing this like 1 for 1. So the length of W and flip W is sort of the same. And I actually do have like flips, right, because I was doing 0 for 1, 1 for 0, right? And note that the question here was design a Turing machine which decides, right? So concretely, that means that the Turing machine M should never loop, and L of M should equal L, right? So, I mean, I definitely have L of M equal L, right? A string gets to the accept state if and only if it looks like W hash flip. And I haven't introduced any infinite loops, right? This is just like when you're taking 2O something. And how do you check that you don't have any infinite loops? Well, you're just like, I'm sure that I didn't introduce any, right? That's kind of the best you can do because the halting problem is undecided, right? So then this is a Turing machine M. This is a Turing machine M, which decides L. Nice. Yeah, question. Oh yeah, decide. Basically, it means that, L of M is equal to L, right? Same thing as FAs, right? So the string allows the machine to get to the accept state if and only if the string is actually an L, right? So that's the same as FAs and PDAs. But also, right, M never loops forever, right? So I don't have any infinite loops, right? So for instance, I don't have something like, I don't know, it's hard to come up with an infinite loop on the spot, but 202 students are so good at it. Yeah, something like this, right? So, A, right, and then A left, something like this, right? So if my input, well, I guess because I'm dealing with zeros, right? So if my input was like 0 and then hash, or maybe this wouldn't work. Let's say if it was like 0, 0, hash 1, 1. Then the string machine loops forever because, it reads the 0, it moves right, it sees a 0, moves left, it sees a 0, moves right, left, and it goes on forever, right? So essentially, by decide, I mean you never have something like this, right? Cool. Nice. Good question. Any other questions? No infinite strings in Company 30. Yeah, talk to me after class if you want to know about infinite strings. Nice. All right. So this is how we're sort of expecting you to think about designing Turing machines that decide languages. So now, what if the language is not decidable? Nice segue, right? So now we're going to enter the realm of undecidability. Right? So another classic question, right? Another classic question is, given L, really, at this point, you're not really going to be given a language anymore. You're really just going to be given a decision problem, right? But, you have to always remember that you can have a corresponding language to a decision problem. It's just all of the strings that encode in binary, for instance, yes instances, right? So this is in sort of in one-to-one correspondence, but it's typically now going to be about decision problems, which are sort of like more intuitive ways of thinking about languages that are undecidable. So you're going to be given some decision problem, let's call it Q, and you're going to be asked to show that Q is undecidable. And so there are two ways that you can do this. One way is a bit harder, right, where you give a reduction. So for instance, from the acceptance or the halting problem, you reduce to Q, right? The other slightly less contrived way is you use Rice's theorem. But notice you cannot always use Rice's theorem to show that something is undecidable, even when it actually is undecidable. It has to be, so Q has to be talking about a property of a language, which I will remind you of in a second, right? Okay, so let's see how we can get a bit more familiar with these types of questions. So by the way, I haven't said it, but like, unless specified, these are all from problem set 6, right? Or really, actually, problem set 6, question 8. So let's do a first one. We want to show that I'm going to give it a name, the at least K acceptance problem is undecidable, where the instruction is using 2, so 2 being Rice, right? So 2 being Rice's theorem, if applicable, and 1 otherwise. Right, so if you can use Rice's theorem, then do it. If you cannot, then you have to give a reduction, right? So that's what we're going to do with the at least K acceptance problem. Now, what is the at least K acceptance problem? The name is hopefully a good hint. So the at least K acceptance problem essentially asks, given a Turing machine M and some integer K, which is strictly positive, at least K acceptance problem, the at least K acceptance problem asks, does M accept at least K strings? Okay. So intuitively, this is undecidable because the acceptance problem is for 1 string and it's already undecidable. So I mean, checking for at least K strings, that's already kind of harder than at least 1, sort of intuitively. Okay. So that's kind of why it's undecidable. Now, first of all, let's ask ourselves, can we use Rice's theorem to show undecidability, to show undecidability? Well, remember the conditions for showing that a problem can be shown to be undecidable via Rice's theorem is, first of all, the decision problem is non-trivial. So there's at least 1 yes instance and at least 1 no instance. And the decision problem is about a property of a language. Is about a property of a language. So the first condition is going to be pretty easy to check. So this definitely is a non-trivial decision problem. Why is it non-trivial? Because I can design 2 Turing machines. So this first one is going to be a yes instance. It's going to be a yes instance because it's going to accept everything. Right, so L of M1 is sigma star. So, I mean, of course, it's a yes instance because, of course, it accepts at least K strings. It accepts all strings, right? Right, so this means that M1 is a yes instance. So when I just write Y, I mean it's a yes instance, right? So this will be abbreviated as is a yes instance. Okay. So I mean now the question is it always true, right? Is at least K always sort of going to be true no matter what the Turing machine? No, because let's consider M2, which, on accept K. Yeah, on input K. Whoa. On input K, or on input X, what M2 is going to do is going to reject all the time, right? So it's going to reject. So then L of M2 is empty. And then if we carefully read at least K, it says, does M accept at least K strings where K is strictly greater than 0, right? Well, no, because, L of M1, the size of L of M2 is 0, right? So it does not accept at least K strings. It doesn't even accept 1, right? So then that means that M2 is a no. So that means that I have a non-trivial decision problem. So yes, this is non-trivial. Nice. Okay, cool. Now, is it a property of a language, right? So to determine whether a decision problem is talking about a property of a language, we essentially want to know if it matters what representative of a language you pick, right? So if you pick the Turing machine M1, which is representing L, right? And M1 evaluates to true. And if this truly is a property of a language, right? If this truly is a decision problem about a property of a language, then it doesn't matter if I pick another representative of L, M2, it should also be true, right? And this should always hold for any Turing machine that accepts the same language as M1. And then similarly, if the answer was actually false to begin with, right? Then it shouldn't matter what representative you pick as long as it's of the same language, then the answer should always be the same. It should always be false in this case, right? So then, okay, formally, how do you actually show this? Just a reminder, you can sort of formally encode this in propositional logic as follows. You want to ensure that for every pair of Turing machines, where the Turing machines accept the same language, the property is satisfied by M1. So this is just, property of decision problem is satisfied if and only if, right, which is kind of representing this kind of idea I just gave, if and only if it's also satisfied by M2, right? So let's see. The property, right, just a reminder here for at least K, essentially the property is does L of M contain at least K strings, right? Because what is L of M? It's the set of strings accepted by M. And what is at least K, right? It's does M accept at least K strings, right? So it's literally, I'm saying the same thing. I'm just sort of representing it formally, right? So then you'll notice that now I've asked this question in terms of L of M. And when you do that, that's nice. That sort of kind of tells you that it probably is a property of a language. So let's illustrate this a bit better. Suppose I have two Turing machines, M1 and M2. They're arbitrary Turing machines. The only thing I know about them is that they accept the same language. Now, suppose that M1 satisfied the property, right? Then what does this mean? This means that M1 accepts at least K strings, right? Which I can just sort of represent a bit more formally as the size of L of M1 is at least K, right? Now, it's very important that I've represented this in terms of L of M1. Why? Because the only thing I know about M1 and M2 is that they accept the same language, right? But that's actually quite useful here, because then that means that since L of M1 is equal to L of M2, I have the same thing about L of M2, right? Since L of M1 is equal to L of M2 by assumption, right? And this, right, remember, this is just a sort of slightly more formal way of saying M2, in this case, M2 accepts at least K strings, right? Which means, right, I'm just going to skip a step. That means that the property is satisfied by M2 as well, right? And then there actually wasn't anything special about the forward direction. The argument is exactly the same in the backward direction. So really, I have an if and only if, right? Which then means that I do indeed, because I do sort of satisfy this propositional statement, I do indeed have a property of a language, right? So therefore, this is a property of a language. So therefore, at least K AP, so is undecidable by Rice's theorem. Nice. Thank you very much, Rice. Cool. Nice. All right. Any questions about this? Let me let you write, actually. That was a bit fast. All right. Doesn't look like we have questions, which, oh, yes. No. The property doesn't have to be the same. It has to be well, I mean, the property, yes, is always the same, actually, right? It's always P. It's not that, so we're not talking about, you have two different properties and they happen to be the same. It's you have the same property and whenever one satisfies it, the other does, and vice versa, right? Yeah. So so like what's different are the Turing machines, right? But the property is the same. Nice, good question. Cool. All right. So let's do another one, right? Where maybe life will not be as easy. So let's do another one. I'm not going to write the instruction. It's exactly the same as before. I'm just going to write the language. The language is going to be reject at least K. So very similar to accept at least K. So you have a Turing machine. You have a positive integer K. But now the decision problem is, does M reject at least K strings? And the reason why I even say that this is probably not going to be as easy as before is because of the thing that hopefully I've said enough that some of you remember, is that in Turing machines, right, rejecting is definitely not the same as not accepting. Okay? Because not accepting, what does not accepting mean for a Turing machine? It means that the string, when you give it to the Turing machine, it doesn't allow it to get to an accept state. So either that's because it explicitly rejects it, or it's because it's looping forever, right? So whereas rejecting is you make a decision. You're not looping forever. You say, no, this is not in the language, right? So these are kind of different. And this is going to be sort of relevant to seeing why you probably can't use Rice's theorem for this. So the first thing that we're going to check is it non-trivial? That's still going to be true, right? Because for instance, I can probably just use exactly the same machines as before. So I'll just say, M1 is on input X accept, right? So same machines as before. And M2 is going to be on input X reject. Well, then here, M2 rejects everything. So of course, this is going to be true no matter what the K. So then this is a no, right? Whereas here, M1 accepts everything. So it never rejects anything, right? So then this is always false no matter what the K. So then here, oh, sorry, I should have said this is a yes. So here I have a no, right? Nice. So it's not trivial. So this isn't where the argument fails. The place where the argument fails is in the following case, right? So remember, for this to be a property of language, for every possible Turing machine, pair of Turing machines, if they accept the same language, then the property is satisfied if and only if it's satisfied by both, right? But now, actually, I'm going to be able to find two Turing machines which accept exactly the same language, but where one is a yes and another one is a no, right? And to do that, I'm going to sort of use this inspiration, right? So I'm going to use M2 as the same as this example, like for non-triviality. So M2 is going to be the same. So I know that this is a yes, and I also know that L of M2 is empty, right? Because it rejects everything, so it doesn't accept anything. So L of M2 is empty. Then I'm going to create a Turing machine M1, which on input X is going to do something a bit different. Can anyone guess what M1 is going to do? Loop, yes, very good. It's going to loop on X, no matter what the X, right? So this is very easy to do in programming. You just say, you know, while true, continue. So just imagine that I'm doing that, but in a Turing machine, right? So then, first of all, what is going to be L of M1? Well, M1 loops on every string, right? So that means that M1 never gets to an accept state because it's looping. So it can't get to the accept state. So L of M1 is still empty, right? So these two Turing machines accept the same language, namely the empty set. But does M1 satisfy the property? Well, let's see. What does the property say? It says, does M reject at least K strings, where K has to be like at least one? Well, no, right? Because M1, right, loops on every string. Looping is not the same as rejecting. Right? Looping is you're looping forever. Rejecting is you've stopped looping and you've told the person, no, I don't want this, right? Looping is you're always thinking about it, okay? So then that means that I have that M1 loops on all strings, which means that M1 never rejects any string, right? So that means that even though these two Turing machines accept the same language, M2 is a yes and M1 is instead a no. Nice. Well, not nice because then we can't use Rice's theorem. So we cannot, so that means, so therefore, cannot use Rice's theorem. That's a bit sad. In fact, what we need to do then to show that this decision problem is undecidable, because it actually is undecidable, is we need to give a reduction. And I will post it and skip it here for time, because I do want to get to the NP complete reductions, and this would delay that. But essentially, to do this, you need to do something like the acceptance problem reduces to the reject at least K problem, right? And I will say, maybe I can just say, right. Okay, so I'll let you think about it. I will post it because it's going to take a bit too long and I really want to get to NP complete reductions. Post afterwards. Okay, but please try to think about it. All right. So any questions about Rice's theorem? No questions. All right. Hopefully that's a good thing. Now, let's get to the final part of the review session, which was also the final part of the class, which is, you know, essentially NP completeness. So NP completeness is an interesting class of decision problems, right? It's decision problems which are decidable, right? So there is a Turing machine that decides it, right? But it's extremely unlikely. So extremely unlikely. That's you. Unlikely that a algorithm exists which decides Q in polynomial time. I say extremely unlikely because, like I said in the previous tutorial, it's still unknown whether P is equal to NP, but I would bet against this. Okay. So the typical questions that you can be sort of given in these types of sort of NP complete exercises is, essentially just give a deterministic Turing machine or a non-deterministic Turing machine that decides Q, like I did in tutorial 12, right? And the other thing that you might be asked is to show that Q is NP complete. So NPC is what I'm using as a shorthand for NP complete. Okay, and so today and for the rest of the session, we're going to focus more on 2. I invite you to look at tutorial 12 recordings for the first thing. So, and I will say that it's kind of interesting to do NP complete reductions here because it necessarily requires you to immediately expand the types of problems that you're going to think of, from like problems about strings to like problems about graphs and problems about all sorts of things. It just so happens that a lot of problems about graphs are NP complete. And so those are typically the ones that are asked in questions for assignments and exams. So, you have to sort of switch gears a little bit and start remembering your discrete math class, right? Okay, so with that being said, let's try to do an exercise. So the exercise, the instruction will be to show that the following decision problem is NP complete. And the decision problem, you might have seen it already if you're taking 360, is the independent set problem, which I will abbreviate as the IS problem. So in the independent set problem, you're essentially given a graph G, which is, a tuple of vertices and edges. And what the independent set decision problem asks is, does G have, so IS for independent set, does G have an independent set of size K? So of size exactly K. Now, if you don't know what an independent set is, the description of the independent set problem given here doesn't really help. So what is an independent set? Let's consider a graph. So this might be familiar to those of you who have already watched the tutorial 12 recording or were at the tutorial 12 session. So this is a graph G. Now, an independent set is a set of vertices where no pair of vertices in that set are connected. Right? So they're independent. Yeah. So for instance, this guy and this guy form an independent set. Right. So V1 and V2. If I put this in a set, then this is an independent set of size 2. Right. Because for every pair of vertices, so V1 and V2, there is no edge. So there does not exist an edge between them. Right. So that's very nice. I have an independent set of size 2. Right. And in general, that's the problem is, can I find a set of vertices of that particular size where none of the vertices are connected by an edge, right? Okay. So I want to show that this is NP complete, right? Which might be a bit surprising because like you start to think, well, it feels like I could maybe design some quadratic algorithm to do this. I just do 4 in pairs of vertices. Doesn't really work, unfortunately. So instead, what I'm going to do is I'm going to show that the independent set problem is NP complete. And to do this, I'm going to force myself to do something. I'm going to force myself to use the vertex cover problem, right? So I'm going to do this by using the vertex cover problem, okay? So the vertex cover problem is another problem about graphs, which I will tell you about right now. So the vertex cover problem is given a graph G. Does G have, you probably guessed it, a vertex cover of size K? Okay, so again, this is not a very helpful description of the vertex cover problem if you don't know what a vertex cover is. So let me remind you of what a vertex cover is. Let me take the same graph, right, and paste it here. So a vertex cover is again a set of vertices, but now it's a set of vertices which should cover all of the edges in my graph, right? So if I take all of the vertices all together, I should be able to cover all of the edges in my graph. So every edge should be connected to at least one of the vertices in the subset of V, right? So for instance, one vertex cover here could be maybe these 3 vertices, right? So maybe V1, V2, V3, right? So why is this a vertex cover? Because I cover all the edges, right? So from V1, I cover this one, this one, this one. From V2, I cover this one, this one, this one. And from V3, I cover this one and this one. So all of my edges are colored in pink, which tells me that I do have a vertex cover of size, in this case, a vertex cover of size 3. The interesting thing here is, for instance, I cannot get a vertex cover size 2. Okay? I can't get a vertex cover size 2 because here I have like a complete graph. So no matter which vertex I pick for the vertex cover, I'm still going to be missing an edge. So that means that I need at least 2 vertices to cover this part of the graph, and then I need at least another one to cover this part, right? So I can't have less than 2 vertices. Whereas maybe if you remember here, can I have an independent set of size 3? Well, here I can't add any other vertices to my independent set, right? Because the graph is fully connected, right? So if I add an extra vertex, right, then I'm going to be connected no matter sort of what pairs of vertices I pick. So it can only be at most one here. And here I of course can't pick both, right? Because then I would be connected, right? So then I can't have an independent set of size 3, for instance, right? It has to be at most 2, right? Of course, you can also always have the trivial independent set of a single vertex. And here you can also always have the trivial vertex cover of all the vertices, right? But the reason why the problem is difficult is because it's for a particular K where, K is not 0 or all of the vertices. Okay, so now these are the 2 problems. It's pretty important to understand the problems before reducing from either of them. Now, let's actually start to show that the independent set problem is NP complete. So to do this, the first thing I want to show is I want to show that the independent set problem is in NP. Okay. And to do this, essentially what you need to do is you need to show that if you had a guess for the independent set problem, if you had a guessed solution for the independent set problem, then you could check it in polynomial time, right? So suppose I'm given some subset V prime of V as the guess to the independent set of size K. How do I check if this is actually a yes instance? Well, I first check that it actually has size K, right? I just count the number of vertices in the set. This is definitely going to be polynomial, right? So linear, actually. Counting how many items I have in a list is linear. The thing that's going to be a little more difficult is checking that this actually is an independent set. For that, I just need a double for loop, right? For every, right? So for V in V prime, for U in V prime. If V is not equal to U, right? Because of course, I mean, if V and U are the same, then they're sort of trivially connected. They're like the same. So if V and U are not the same, then check that VU is not an edge in the graph G that you're sort of looking at, right? And so if the check fails, then you return false or you reject. Otherwise, you go through this entire double for loop. At the end, if you've never returned false, then you can exit the for loop, 2 for loops, and return true, right? So then, an analysis of this double for loop is, this is at most size of V, this is at most size of V, so it's quadratic in V. So this is O of V square, which is polynomial, right? So yes, this is a polynomial time checker. Which implies that independent set is in MP. Okay. Nice. It's so wild that you have to do this in 330, but it's like 4 loops in 330. Anyways, I shouldn't complain. Okay, so this is how you show that it's in NP. Is this okay with everyone? Okay, hopefully blank stares are good. Let's move on to the slightly more challenging part. I need to show that now the independent set problem is NP hard. And to do this, what I need to do is I need to reduce it from a known NP hard problem. And sort of that's why I introduced the vertex cover problem at the beginning, because what I'm going to do is I'm going to reduce it from the vertex cover problem. So I'm going to reduce the vertex cover problem to the independent set problem. And so as a reminder, what does this mean to reduce from one problem to another? In this case, it means that I want to create a solver, a polynomial time solver for the vertex cover problem with a polynomial time solver for the independent set problem. Why? Because if I do this, then I can argue that the independent set cannot be a polynomial unless P is equal to NP, because it would mean that vertex cover is also polynomial, right? And then that would mean that sort of NP and NP are sort of the same, right? Which I mean would be surprising. Okay, so I want to create a vertex cover solver, right? What should the vertex cover solver do? It should take an instance of the vertex cover problem, so a graph and some positive integer k. And the vertex cover solver should say yes if, right, G has a vertex cover size k, and it should say no otherwise. But now, how am I actually going to create the solver? I'm going to create the solver by taking the instance of the vertex cover problem and converting it, or instance modifying it. So this is the instance modification. Which, this is a polynomial time reduction, so it should be polynomial in time, right? So it should convert G and K to an instance of the independent set problem, right? So it should convert GK to G prime K prime, right? And it should do this such that if I give it to an independent set solver, then the answer to the independent set problem instance should be yes, if and only if it was yes for the vertex cover problem, right? So I should design the instance modifier such that the answer to the vertex cover problem for G and K is yes, if and only if the answer to the independent set problem for G prime and K prime is yes. Why do I want to do this? Because I'm using the independent set solver. I'm using the independent set solver. So I know that this is always going to say the right answer. And so it should only say the right answer if it matches the sort of answer of the original input, right? The other way, right, the other way that I've also described this in the tutorial is, if I have a yes answer going in to the solver, then I should have a yes answer going out. And if I have a no going in, then I should have a no going out. But this is exactly the same as yes, if and only if yes, right? Because I'm just taking the contrapositive of this. So there's just two different ways of looking at the problem. You can either argue it this way or this way. Typically, in NP-complete reductions, you usually do it this way. Okay. So that's what we're going to do. Okay. Right? So hopefully the objective at this point is clear, right? The objective is now, what I want to do is I want to design the instance modifier, right? I want to design it such that it takes G and K, it does something in polynomial time, so, square, cubic, whatever, as long as it's polynomial, such that you get G prime and K prime, where when you give G prime and K prime to the solver here, it'll say yes, if and only if the actual answer here was yes. If it was no, then it should say no, right? So then you actually have a correct VC solver, okay? So that's what I want to do. And to do this, I'm going to make an observation between, an observation on the connection between the independent set and the vertex cover problem. So this is a common way of doing these reductions. So this is a common reduction technique. Is you firstly observe some relation between the problems between, so if you're trying to do, P polynomial time reduces to Q, so you observe some relation between P and Q, and then you sort of implement that relation in the instance modifier. So you implement 1 in the instance modifier. Okay. So what's this observation going to be? It's very difficult to sort of just think of this in 30 seconds, right? So it took me a while also. So, whenever it comes to these types of problems, just, take it easy, take like a good 30 minutes to think about it. And if you get stumped, then maybe check the solutions. But it always helps if you're doing this to sort of look at a concrete example, right? So that's kind of how I always sort of look at the relations between the two problems, is I try to look at concrete examples. So to do that, let's consider the graph that I introduced before, right? And let's consider its vertex cover, right? So we know that this graph has a vertex cover of size 3, right? That vertex cover is, well, one of those vertex covers is this one, right? This is just from before, right? So this is a vertex cover, right? Okay. Now, what am I going to observe? I'm going to observe that, suppose I just take this graph and I copy it, right? And I consider the vertices not in the vertex cover, right? So I look at this vertex and I look at this vertex. Then these two vertices form an independent set, right? And they must form an independent set because if there was an edge between them, then it wouldn't be covered in the initial vertex cover. So then I would have an incorrect vertex cover. Nice. All right. So that means that I have an observation between these two problems. It's namely that I should take the complement of the vertex cover, and that will give me an independent set, right? So here I have an independent set of size 2. And the general observation that I'm going to make, which I'll state as a lemma, is that G has a vertex cover of size K if and only if G has an independent set of size, well, the total number of vertices minus that set. So the total number of vertices minus k, right? Okay. And, the quick argument, which I'll give for this, like probably, very likely, if you're doing this in an exam and you sort of state a lemma like this, then you're going to have to show the correctness of the lemma, right? Because, JL wants you to be rigorous. But typically, it'll be something that's pretty doable. Like, for instance, this proof is going to be pretty doable. Why is it pretty doable? Let me just give you the forward direction. Let's start with the forward direction. So suppose G has a vertex cover size k, right? So, G has a vertex cover V prime, where V prime is equal to k, or the size of V prime is equal to k. So, I take G, and, I have my vertices in my vertex cover. So maybe this is V prime, right? Then what I do is I say, okay, let me pick two vertices. So let me pick two vertices, U and V, which are not in V prime, right? So let me pick two vertices, U and V, which are in V prime complement, right? Then there cannot exist an edge in the graph, in the set of edges of the graph, which connect U and V, right? Why, right? Why? Because otherwise, so let's assume by contradiction, right? Otherwise, right, you would have a connection between U and V, right? But both of these are not in the initial vertex cover, right? Which means that V prime is an incorrect vertex cover, right? It misses an edge, right? Which is a contradiction because, I'm assuming in my premise that I have a correct vertex cover. So then I get a contradiction, right? Which tells me that the otherwise can't be true, right? That means that there cannot be an edge between these two arbitrary vertices in V complement, right? But these two arbitrary vertices were arbitrary, right? So this means that this is true for any pair of vertices in V prime complement, right? Because I'm just taking an arbitrary thing and I'm making it a for all, right? So that means that for every pair of vertices in V prime complement, the same statement holds, right? There does not exist an edge between U and V, right? And this is exactly the definition of an independent set, right? What's an independent set? It's a set of vertices, right? It's a set of vertices where there is no edge between any of those vertices, right? So that means, very nice, that means that V prime complement is an independent set. And it has size, well, it has size, the total number of vertices minus the number of vertices in V prime. V prime has k vertices, so it's V minus k, which is exactly what I was trying to show in the forward direction. Nice. Right? And the backward direction is going to be exactly the same argument, but just backwards. Right? So I'm going to skip it just because it's so similar. So this will be a similar argument. Okay? So then why is this useful? Right? Why is this useful? Because I can now use this lemma for the instance modification. Right? So remember, I'm just going to quickly scroll up, but don't worry, I'll come back down. Ah, yeah. So let me copy this. Okay, right. So remember, I wanted to do something like this, right? Where I preserved, yes to yes, no to no. But now the lemma tells me how to do this, right? I'm just going to say, make G prime the same as G, right? and make K prime V minus K, right? And by the lemma, I know that the answer to this is yes, if and only if the answer to this is yes, right? But that's the instance that I'm giving to the independent set solve. Right? Nice. Okay, cool. So then this is going to be the instance modification. It's polynomial in time because all I'm doing is I'm just copying a graph, right? So, you know, at most this is V plus E, right? And this is just the cost of copying. Okay, right? So then this is my instance modification. The last thing I'll do is just I'll argue a bit more formally correctness. So I'll just argue a bit more formally correctness. So to argue correctness, I essentially have to show, sorry for scrolling, I have to show this is true, right? So let's see. The answer to the vertex covering problem for G and K is yes. If and only if G has a vertex cover of size K, right? I mean, that's what it means to be S instance to VC. And then by the lemma, this is true if and only if G prime, which is actually equal to G, as a reminder, has an independent set of size K prime, because this is, as a reminder, V minus K, right? So this is by the lemma. And then because G prime and K prime are what I'm giving to the independent set solver, then, whoopsies, why the heck did I do that? I'm really getting tired. Then this is true if and only if the answer to the independent set problem for G prime and K prime is yes, right? So I can essentially create a vertex cover solver with an independent set solver. Nice. So that means, and I can do that in polynomial time, which means that the vertex cover problem, polynomial time reduces to the independent set problem. And so therefore, since VC is NP hard, so is the independent set problem. And this implies that the independent set problem is in NP and NP hard. And so therefore, independent set is NP complete. Nice. Okay. All right. Any questions about this? Okay. I think I have one more in me. But I don't think I can do more than that. So let me just shake this off my wrist. All right. So I'm going to do one last one. It's going to be another NP complete reduction. It's actually going to be the same sort of goal. I want to show that independent set is NP complete, but I'm going to use a different problem to reduce to it for reasons that I will only tell to myself. Okay, so hopefully people have finished copying. Now I'm going to do the same thing, right? So this is going to be the same example. This is actually also an exercise in problem set 6. It's problem set 6, I think question 8, where it shows you to, where it tells you to show that independent set. So show that independent set is NP complete, but this time using, right, using the fact that 3-sat is NP hard, right? So this first exercise I did was kind of nice because, you know, you had a graph to a graph. Now this one is going to be a little less nice because you have 3-sat, which is not a graph, and you got to get it to a graph. So let's see how we're going to do this. The nice thing about this exercise is that I'm using independent set again, so I'm not going to re-explain to you what independent set is. And the other nice thing is that we already know that independent set is in NP, right? So, you know, we already know that IS is in NP, see above. So the only thing that we want to do is we want to show that it's NP hard. But now instead of reducing it from vertex cover, we want to reduce it from 3SAT. Right? And maybe just a reminder of 3SAT, right? So the 3SAT problem is, given a Boolean formula phi in 3CNF, right? Does phi have a satisfying assignment? Right? So, what does this mean? What is 3CNF and what is SAT? So a Boolean formula phi is in 3CNF if it's in conjunctive normal form. So if it's the conjunction of several clauses which are themselves sort of disjunction of individual variables. So for instance, I have one clause, I have another clause, I have a third clause, and so on, right? So these are clauses. And I always have an and here, so I have an and operator. And within this clause, I have disjunctions, right? So I have maybe like x1 or x2 or not x3, right? And it's in 3CNF if I always have 3 variables in my clauses, right? So 3CNF is because I have 3 variables per clause. Or sometimes, they're called literals, so let me use the proper, let's not make the theoretical computer scientists mad. Cool. All right. So I have this Boolean formula. And then I essentially want to know, does it have a SAT assignment? In other words, is it possible, right? Is it possible to assign, x1, x2, and all of the other variables in the formula phi to truth values, right? Such that the entire formula phi is true, right? So that's what it means to find a satisfying assignment, right? Okay. So this is very different from a graph problem, right? It's about, can I find the truth values of variables in such a way that I satisfy a formula. But there's a sort of classic trick of converting a problem about graphs to a problem about Boolean formulas and vice versa. In this case, it's the vice versa direction because we want 3 sats to independent set. So we want to create a 3-sat solver, right? And to create this 3-sat solver, what we want to do is, we have an instance of 3-sat, right? We want to instance modify it in polynomial time such that we get an instance of independent set, so some graph and some integer k, where when you give that graph and that integer k to the independent set solver, then it says yes if and only if the answer to the 3-sat problem is yes, right? So if and only if I actually have a satisfying assignment. Otherwise, it should say no. Okay. So this is a bit tricky, but it's not too bad if we consider the sort of classic. So this is a classic sort of trick for doing something like SAT to a problem about graphs. And the classic trick is you take the clauses and you make them 3 cliques, right? So you take phi. For instance, maybe phi, the first clause in phi is x1 or x2 or not x3, right? Maybe you have others. But the general thing is, you take the first clause and you make it into a 3 clique in the graph. So this is going to be my instance modification. I'm going to create a 3 clique, x1, x2, and not x3. Okay. And then I'm going to do this for every clause, right? I'm going to do this for every clause in my graph. So for every clause in my Boolean formula phi. So for every clause in phi, right? So that clause is, L1 or L2 or L3. Then I'm going to create, L1, L2, and L3 in my graph. right? So I've taken the Boolean formula, and now at least I have a graph, right? But it's not enough to just convert it to a graph. I need to have a yes goes to a yes, and a no goes to a no, right? Because I need a correct sort of instance. I need a correct solver of the 3-sat problem. But at least I've gotten the types right? So that's kind of nice. So I have my graph G, and this construction, maybe just to get it out of the way, this construction is also going to be polynomial, because what I'm doing is, for every clause in phi, I'm just adding a 3-clique, right? So that's kind of like linear in the number of clauses I have, right? So this is definitely going to be polynomial. It's going to be linear in the size of phi, right? Where size of phi, this is number of clauses. Okay, so that's nice. And maybe, the other thing is, what am I going to give to the independent set solver, right? What is going to be K? Well, at this point, that's when I can actually start talking about maybe the connection between G and phi. The connection between G and phi should be that, for every clique, I should be able to sort of select one vertex that should make the clause true, right? That's kind of what I kind of want to do in this conversion. I want to sort of take every clause, put it into a 3-clique, such that the independent set is going to be, one vertex from here, one vertex from here, one vertex from the other triangle, one other from the other triangle. And all of those guys together are going to form a sort of yes instance to the initial, independent set problem, or the 3-sat problem. Okay. So then that means that my K, what should my K be? My K should be, well, the number of clauses I have in my original Boolean formula phi, right? So it should be the number of clauses in phi, right? Because I want an independent set of size, the number of clauses in phi, because I want, for each triangle to have sort of one variable that's going to allow me to satisfy the corresponding clause, right? That's how I'm trying to connect these two problems together. Okay. So this is going to be my first attempt, right? This is my first attempt. I just have this graph G. I have my triangles, very nice. And I have this to be K. So let's see what happens, right? I'm going to go a bit over time. I'm going to have to need 10 extra minutes, but hopefully it'll be worth it. Yeah. Okay. So let's see if attempt 1 works. So let's see if attempt 1 works, where, the attempt is I take phi, I have, my Boolean formula, and I'm converting this to G, where G is my collection of triangles, right? Right. And K is sort of the number or the size of phi. So to check correctness, essentially what I need to check is the answer of the 3-sat problem to phi yes if and only if the answer to the independent set problem of G and K yes, right? So I want to check this, right? Because if I have this and I have a correct 3-sat solver, if I don't, then I have to refine it. So let's see. The forward direction is going to work out, right? Why is the forward direction going to work out? Because, in my graph G, I definitely have an independent set of size K, right? I definitely have an independent set of size K. I take one vertex from each of the triangles, right? One vertex from each of the triangles. I put this in a set V prime, and this forms an independent set of size K, right? Why? Because each of these vertices are not connected, right? Because I just have the triangles, right? That's the only connections I have. So that means that I definitely do have, right? I definitely do have that the answer to the independent set problem is going to be yes, right? Okay, good to know. But this is not really going to work in the backward direction. So it's not really going to work that, if I have an independent set, then I can use the independent set as the solution to the 3-sat problem. Why is it not going to work? Because if I have the answer to the independent set is yes, right? Then, there's multiple possible answers that I could have, right? One of them could be maybe I have, my triangles, and the independent set is maybe, I have x3 and I have not x3, and then both of these vertices are in the independent set, right? But then this is not going to be a valid solution for 3-sat, right? I'm not going to be able to say, well, I have a solution to 3-sat. I'm just going to make x3 equal to true and not x3 equal to true, because if x3 is true, then not x3 is false. And if not x3 is true, then x3 is false, right? So then I won't have, right? I cannot, so in this case, right? In this case, I cannot derive a solution to 3-sat from G, since, for instance, not x3 is true and x3 is true. These both cannot be true, right? So this is impossible, right? And in fact, a bit more generally, why doesn't this work? It's because there's actually always an independent set of size k, no matter whether the answer to 3-sat is yes or no, right? I can always find, right? The answer is always going to be yes. I just pick a bunch of vertices, one from each triangle. That's always an independent set, even if phi is false, right? Even if I can never satisfy phi, right? So that means that, so let me just actually write that. So I'll write, in fact, given the current construction, so given the current instance modification, the answer to the independent set sort of instance, G and K, is always going to be yes for any phi, right? So that means that I don't actually have much of a solver. I just have a Turing machine that always says yes. It's kind of a flop, right? That's not really what I want. I want one that says yes only when the answer is truly yes. So then what's going to be the fix? The fix is essentially just to avoid this problem, right? So this is the sort of root of the problem. So I'm essentially going to try to create a slightly more refined instance modification where I always avoid this, right? How am I going to do this? I'm just going to connect vertices between two triangles if they're the sort of negation of each other, right? And that's going to be my fix for this, right? So the fix is going to be to, force the independent set solution to be a solution to 3-sat. And so how am I going to do this? I need to essentially avoid the possibility that in the independent set solution, I have x3 and not x3 in my independent set, right? So I need to avoid this, right? Avoid this, so avoid independent set, so x3 and not x3 in independent set. So to avoid. Okay, I want to avoid this. Okay, how am I going to do this? I'm just going to connect the literals that are negations of each other in the graph, right? So then the new construction for G is going to be very similar to the one before. So for every clause L1, L2, L3 in phi, add a triangle in G, or a 3-clique, but it's fun to call them triangles. And then the second thing is for every Li, not Li, in G as vertices, add Li, add an edge between Li and not Li, right? So for instance, if I have like x1, not x1, and not x1 here, then, this is the first part of the construction. The second part of the construction is I'm going to connect these guys, right? So then, this is linear in the size of phi. And then this part, like a double for loop maybe, right? So for every, triangle I have, I check whether I have sort of negations in any of the other triangles. If yes, then I connect them, right? So I have, for every triangle and for every vertex in there, check if I have any others in the rest of the graph. So this is going to be, roughly quadratic, right? That was a poor time complexity analysis, I grant you, but it's good enough for my knees, which are about to buckle. The nice thing, though, give me a second. The nice thing, though, is that now this works. So now I can argue the correctness. So this is G, right? And K is going to be the number of clauses in phi, right? Same K as before. But now I actually do have a correctness, meaning I do have yes, if and only if yes. So I'm going to argue this. So if the answer to the 3-sat problem is yes, what does this mean? That means that there exists an assignment, let's call this assignment A, of Boolean variables, right? x1, so maybe x1 to true, x2 to false, and so on, such that phi is true. So then what I need to prove is that I can actually, I actually do have an independent set of size k, right? And to do this, I can just construct the independent set. So it's a proof by construction, right? So I can argue that I have an independent set. So an independent set of size k exists in G, right? What is it? Right? Well, essentially, it's defined this way. So for each triangle, right, L1, L2, L3, only circle one literal, so one of L1, L2, L3, which is true in the assignment A. So in which is true, is true in A. Right, so I go through each, right, so I have my graph, right, my graph G, I have all my triangles, I go through each of the triangles, each triangle corresponds to a clause. For each clause, there must be at least one of the literals that are true, because I mean, it's a disjunction, it's a conjunction, right? So it's clause 1 and clause 2 and clause 3 and so on. So each of the clauses has to be true. If each of the clauses has to be true, at least one of these guys for each clause has to be true. So I just pick one of them, right? I don't pick two, because if I pick two, then I don't have an independent set. I just pick exactly one, right? And I definitely can do this because I know that I have a 3-sat solution, right? Nice, right? So then only circle one, which is an assignment. Okay. And then this is, right, my argument is that this is an independent set of size phi, right? Because the only way that Li and Lj, right, so the only way that it would not be an independent set is if two of the vertices I circled, so maybe Li and Lj, were connected. But if Li and Lj were connected by the construction, right, I only connected them in the construction if Li was the negation of itself, right? So then because Li and Lj would imply that Li or Lj is equal to not Li, right? But then remember, I only circled if these both were true, which cannot possibly occur if I have this, right? Because then it means that either, so either LJ is not true, so then it's false, in which case I circled incorrectly before, but I'm assuming I circled correctly. Or, Li is, or sorry, let's see. Or, Li is, well, it has to be true. Oh, I think this is already a contradiction, right? So, I mean, I know that Li has to be true, right? Right, but Lj must be true to have been circled, right? Because I was only circling these guys, right? Here, I only circled if L1 actually evaluated to true in the assignment, right? So, so then that means that I can't possibly have that this literal is false by construction, right? So that means that we do indeed have, right? We do indeed have, because the argument here was that this is an independent set because this is impossible, right? There's no edge between Li and Lj, right? Which implies that, the V prime, which is the different literals, so L1, L2, L3, each from different triangles. So this forms an independent set of size k. So therefore, the answer to the independent set problem for G and K is yes. Right, so I have a yes goes to a yes. Okay. Now let's see. Do I have the strength to do the other direct? Okay, it's not so bad. Okay, let me quickly, I know I'm way over time, but let me just quickly do the other direction, right? So suppose, now the other direction is to say, if this is yes, then I also have yes for the three-side problem. So if this is yes, right, then what does this mean? It means that I have an independent set for my graph G of size k. But what is my graph G? It's like these triangles, right? And these triangles are kind of like connected. If I have Li, if Li is in one three-clique and not Li is in another, right? And so then the independent set is going to be some sort of circling of these vertices, where I'm never going to circle both of these, right? I'm going to circle maybe one, but never both, right? So then, given this independent set of size k, right, what I can do is I can create a satisfying assignment. I can say if Li is circled and maybe Li is equal to xi, right, then make xi true in phi. If it's not xi, then make it false, right? So then I have essentially one true for every clause, right? The remaining literals, like maybe I have some remaining variables that I didn't touch yet, I'm just going to assign them to true, right? Because I don't really care. So then the remaining variables are assigned to true, because it doesn't really matter. I already know that for every clause I have an Li which is true because I'm going through this sort of assignment. And so therefore, this is a three-sat solution because for every clause in phi, there exists an Li in that clause such that Li is true, and you never have like a contradicting assignment, right? And there does not exist contradicting assignments, right? So a contradicting assignment would be, this is true because in one case xi is true, and another case it's because xi is false, right? So this can't happen because these two guys would have been connected in the graph G, and so they actually wouldn't have been both in the independent set, right? So that means that my answer to the 3-sat problem is yes. So I have a yes if and only a yes. And so then 3-sat reduces in polynomial time to independent set. So therefore, again, we have a double result. Independent set is doubly NP complete. Nice. All right. Whew. Only 15 minutes over. All right. So yeah, thanks for coming. I will be at the final because Jérôme will be on holiday. So I'll be there to answer your questions. So yeah, thanks a lot. And then, okay, thanks very much. Thank you. And good luck with this final and all your other finals.